In this video, we're going to go through some problems from section 6.1 and discuss how to solve them. This will be a relatively fast video since there's not a whole lot of new material in here that you probably didn't understand. Later in this chapter, there will be things that will be far more difficult and we'll take more time on those. The first problem says, identify whether the statement represents an exponential function. Remember that an exponential function goes faster and faster as time goes on, or slower and slower as time goes on. So the rate of change is increasing as time goes forward, or the rate of change is decreasing as time goes forward. That means the change is not always the same from one time period to the next. This question says, the average annual population increase of a pack of wolves is 24. The key words here are average and annual. That means that every single year, the pack of wolves increases by 24. In other words, it's the same in each time period. Because it's the same in each time period, this is not an exponential function. Let's take a look at the next problem. In the next problem, it says, for each year t, the population of a forest of trees, call it forest A, is represented by the function a of t is equal to 120 times the quantity 1.022 raised to the t power. In a neighboring forest, call it forest B, the population of the same type of tree is represented by the function b of t, which is equal to 83 times the quantity 1.026 raised to the t power. The question wants to know which forest population is growing at a faster rate. Since both have a power of t, that's the same in both equations. That then will not be what is affecting the rate of growth. In this case, what will affect the rate of growth is the base of the exponential. In forest A, the base of the exponential is the 1.022. Remember that by order of operation, exponentials are done before the multiplication by 120. Remember that it is Pemdas, parentheses, then exponents, then multiplication and division from left to right, then addition and subtraction. On forest B's equation, we have 1.026 as the base. Therefore, the base of forest B is actually larger than the base of forest A. And that means that forest B is the one that's growing at a faster rate because it has a larger base. What about the next question? Which forest had a greater number of trees initially? When they say initially, they mean when t is equal to 0. So when you're thinking about when t is equal to 0, you want to look back at the equation and imagine putting 0 in place of t. Anything raised to the 0 power except 0 is the number 1. So that means that for forest A of 0 would be equal to 120 times 1.022 raised to the 0th power, which is 120 times 1. That means that the value is 120 trees initially. If we apply the same process to the next part, when we're looking at forest B, oops, and I need to use a B there, we've got B of 0 is equal to 83 times 1.026, the higher rate, the higher base, raised to the 0th power. And that would be 83 times the number 1, which is 83. That means that forest A initially had more trees, but forest B was growing at a faster rate. So forest A had more trees to start with. How many more trees? Well, that would be 120 minus 83. Remember, when you subtract, that you can borrow from the terms next to it. That would make this 11, and that would make that 10. 10 minus 3 would give us 7, and 11 minus 8 gives us 3. That would be 37 trees more in forest A than in forest B. The last part to this question is, assuming the population growth models continue to represent the growth of the forests, which forest will have a greater number of trees after 20 years, round to the nearest tree? To compute this, what we need to do is to compute A of 20 and compare that amount to B of 20. So when we're looking at A of 20 and B of 20, what we have is A of 20 is going to be equal to 120 times the quantity of 1.022 raised to the 20th power. You will want to grab your calculator to figure this part out. If we're going to do that, what we need to find is the following. To imitate the order of operations, you will first take the 1.022 and enter it into the calculator. Then there's a button on your calculator somewhere that probably says x to the y or y to the x. It may also look like a caret symbol or a housetop symbol. This will give you the power. When we click that button, we can raise it to the 20th power. You should now have on your calculator something like 1.5453181887, and it keeps going from there. Now take that number and multiply by 120. Your final result is approximately 185.438. Rounding to the nearest tree would be about 185 trees. Let's now repeat the process on forest B's information. That means that we need to take the number 20 and plug it into the B forest equation. 83 times 1.026 raised to the t power, and t will be 20. So that will give us 83 times 1.026 raised to the 20th. Take your calculator now and put in 1.026, hit the x to the y or y to the x or the caret symbol button to get the power and enter 20, then hit the equals or the enter button. You should have 1.67088751 and so on. Then take that number and multiply by 83 to imitate the order of operations. This is about 138.68, so we'll round up to about 139. Now, the next question says, by how many trees? We can take the 185 and we can subtract the 139 from it. When we do that, we'll have to borrow, and this will become 17. 15 minus 9 gives us 6. 17 minus 13 is 4. So roughly, this is 46 additional trees. Let's take a look now at the next problem. In the next problem, it says determine whether the equation represents exponential growth, exponential decay, or neither one. When we look at this, we have 600 times 0.93 raised to the t power. The 600 looks like a large number, which might make you think that this is going to grow, but that's not what determines growth or decay. It's the base of this problem. And the base of this exponential is 0.93. Because the base is less than 1, that means it's a fraction. And when the fraction is raised to the t power, it will decay. That means as time goes on, it gets smaller and smaller, and the rate of decay gets smaller each time. And that means that this is a decay problem. Let's take a look now at our next problem. It says determine whether the equation represents exponential growth, exponential decay, or neither one. In this case, notice that our base is 1 minus t inside the parentheses. The 500 is not a part of the base. It's being multiplied by the parentheses. The base is the parentheses. The power, however, is a 5. And because the power is not the variable, this is not an exponential equation. Exponential equations have constants for the base and powers for the, or variables for the power. Just like in this problem, we had a constant 0.93 for the base and a variable for the power. That makes it exponential. This problem is not an exponential problem. It's not exponential growth or exponential decay, so it's neither. Let's take a look at the next problem. Determine whether the equation represents exponential growth, exponential decay, or neither. In this particular problem, we have 500 multiplied by 1.08 raised to the 1 divided by x power. In this particular problem, what we have is a power that does have the variable in it, but the power is not either exponential growth or exponential decay, because exponential growth would have the 1.08 raised to the x power, and exponential decay would have a fraction instead of a number larger than 1 raised to the x power. Because the exponent is 1 over x, this means that it is neither exponential growth nor exponential decay, but it is an exponential type problem. In this case, we'll select neither, since it is neither growth nor decay. Let's take a look at our next problem. Find the formula for an exponential function that passes through the two given points. First off, we can see that we know that the first amount that we started with when time was 0 was 7. That means that we must have some constant base being raised to a variable power of x and being multiplied by 7. So far we know that we have 7 times some number, which is unknown, raised to the x power. Again, we know that because the variable x will be 0 in the initial time period when time equals 0, and 7 tells us how many there were present at that time period. Now, how can we figure out the next thing? This says that I take the number and I raise it to the 4th power. I get 567 after I then multiply it by 7. In other words, if I take the number 7 and I multiply it by my unknown raised to the 4th power, I should come up with 567. Order of operations, again, tells you that you take the unknown to the 4th power first, then multiply by 7. To isolate the unknown, the first thing we'll do is divide both sides of the equation by 7. When we divide both sides of the equation by 7, that will leave us with the equation of 56 or 567 divided by 7. I can't talk tonight. So this gives us the unknown raised to the 4th power equal to 81. Then we have to ask ourselves the question, what number raised to the 4th power gives us 81? So you can take the 4th root of both sides if you want to find the solution. The 4th root of something to the 4th power will give me the something by itself. On this side, I take the 4th root of 81, and I know that 81 is 3 to the 4th, and I come up with the unknown being 3. Therefore, my equation should be f of x equal to 7 times the base 3 raised to the x power. That's my exponential equation. Let's look at the next problem. In the next problem, we do not have the initial value. What we have is the value at 2 different points in time. How are we going to solve this particular problem? First, we need to figure out what the rate of growth is. In this particular problem, our 2 points are -2, 5 and 3, 1. Neither one of these has 0 as the first coordinate, so neither one of them is the initial condition. This means that we have two equations, and we'll write them like this. One equation is y equal a times our unknown base being raised to the -2 power. The second equation is our y equals our unknown initial value a times the unknown base being raised to the third power. When we're done with each equation, we end up with the y value. So when the power is -2, our y value ends up being 5. This gives us the value that 5 is equal to ab to the -2, and that 1 is equal to ab to the third power. Now, the next thing that we want to do is we want to take these two equations and solve them together so that we can find the solution for a and b. We need at least two equations since we have two unknowns. We're going to solve for a from each of the equations, and then we'll set our a's equal to each other. In the first equation, I'm going to divide both sides by b to the -2, or I can think of it as multiplying by b squared. You can think of it either way. Both will give you the correct value. If you think of it as multiplying by b squared, remember that when the bases are the same, you add the exponents, and -2 plus 2 gives me 0, and anything to the 0 except 0 is the number 1. This means that I've isolated the a in the left equation so that a is equal to 5 times b squared. Now let's isolate the a in the right equation. For the right side, I'm going to make the choice to divide by b cubed. If I divide both sides by b cubed, I can then write this as a equal 1 over b cubed. Remember that 1 over b cubed can also be written as b to the -3 power, since a negative exponent means that it would have been in the denominator with a positive exponent. Now this is a and this is a, but these represent the same a. And since a is equal to itself, I can set the two sides equal to each other. And this gives me that 5b squared has to be equal to b to the -3. Now that I have this, I can solve the equation and I can find b. In this case, what I want to do is I want to get my two b factors together. To do that, I'm going to multiply both sides of this equation by b to the third. This will move it from the right side to the left side. And when I multiply by b to the third, remember that on the right, the bases are the same, both b. So I add the powers, -3 plus 3 is 0. Anything to the 0th power except 0 is the number 1. That leaves me a 1 on the right-hand side, and 5 times the combined factor of b cubed times b squared. Since the bases are both b, I add the powers again, and I get that b cubed times b squared is b to the 5th. This tells me that 5b to the 5th equals 1. The next thing I can do is divide both sides of the equation by 5. When I divide by 5, this tells me that b to the 5th is equal to 1/5. The next thing I would do to find b would be to take the 5th root. The 5th root is the same as the 1/5 power. And this means from here that I can represent b as 1/5 raised to the 1/5 power. Or I could have written it as the 5th root of 1/5. Because we're working with exponents, we'll use the exponent form of it here. If that's my base and is being raised to the 1/5 power, what does that give me when I take it and I try to plug it in to find the value of A. To find the value of A, I can return to one of the original two equations that I had up here, and I can plug in what I know now to be my B value. I think this one here is a simpler problem since the exponent is positive on the B and the number on the right is a 1. So I'm going to substitute this into that equation. So I will substitute B into 1 equals A, B to the third power. So I have 1 equals A times 1/5 being raised to the 1/5 power. Now, that also is being raised to the third power because the base B is 1/5 to the 1/5 and the power on it is the third. What do you do when you have one base, but it has two powers on it? The rule is multiply the powers. This then tells me, moving down to the next page where I've got a little bit more room, this then tells me that what I have is 1 is equal to 1/5 with the A on the outside, and the 1/5 is raised to the 3/5 power. Now, how can I find the solution for A? In order to find the value of A, what I need to do is move this to the other side of the equation. To move it to the other side of the equation, I need to divide by it. So if I divide by it, I can get the following value: 1/5 raised to the 3/5 divided on both sides. Now that I have A isolated, I need to think about what 1 divided by 1/5 raised to the 3/5 power really means. I have 1/5 raised to the 3/5 power. What does that mean for me? Well, I know that I've got 1/5, and I can think of the 5 as 5 to the first power. I know that when I have something in the bottom or in the denominator, I can move it to the numerator by changing the sign of the exponent. That will let me write this as 1/5 to the -1 being raised to the 3/5 power. Now that I have that raised to the 3/5 power, the next thing that I could do is I could say, okay, I should multiply these two together since I have one base and two powers on it. Then I multiply the powers together, and that will give me 1/5 to the -3/5. But the negative power tells me it could be moved to the numerator, and therefore A is 5 to the 3/5 power. This gives me a final equation of 5 to the 3/5 times 1/5 raised to the x/5 power. Since I need the variable to show up in here, the power that I found for the base was originally 1/5 to the 1/5, which means that's the base. And I can multiply the x by the 1/5 to get x/5. This is the final form of my answer. Let's take a look at another problem. In our next problem, it states, determine whether the table could represent a function that is linear, exponential, or neither one. In looking at this example right here, I look at the values to see whether they're decreasing or increasing by the same amount each time. If they're increasing or decreasing by the same amount each time, then it's linear. When I look at this, I can see that the values are going down. 65, then 40, then 15, then -10. Not only that, but they're going down by the same amount. It decreases from 65 to 40, a decrease of 25. Then it decreases from 40 to 15, which is also a decrease of 25. And then it decreases from 15 to -10, which is also a decrease of 25. Since the decrease is the same every time, That makes it linear. Let's look at the next problem. Could this table represent a function that is linear, exponential, or neither? In this problem, we have 25, 0, -25, and -50. Our choices are again linear, exponential, and neither. In looking at this problem, I can see that the values are going down. The first pair goes from 25 to 0, a decrease of 25. The next pair is from 0 to -25, also a decrease of 25. And the last pair is a decrease from -25 to -50, which is also a decrease of 25. This is the same function as the previous one, but starting at a different value. In other words, the rate of change is the same, it's decreasing by 25. That makes this one linear as well. Let's take a look at the next problem. In the next problem, it states, determine whether the table could represent a function that is linear, exponential, or neither. Now we have another table and we're looking at these values here. We have a change from 22 to 82, which is an increase of 60. From 82 to 182 is an increase of 100. And then the final increase from 182 to 322 is an increase of 140. So clearly it's going up in value, but not by the same amount each time. We'll know whether it's exponential if it's the same percentage of increase. So in other words, when we're looking at this, we need to know what percent of 82 is 22. So we ask ourselves the question, what percent of 22 is 82? To find the answer to this question, what we need to do is to answer the question, what percent of 82 is 22? To do a percentage problem, translate the words into mathematics. What percent means question mark. Of means multiply. Something times 82 is means equals, and then we have 22. To find the percentage, what we need to do is divide 22 by 82, and then to get a percent, we'll multiply it by 100%. The number that we get when we take 22 and divide by 82 is 11 out of 41, which is the same as 0.268, roughly. We multiply that by 100% to get a change of 26.8%. In order for this to be exponential, every pair of numbers has to go up by exactly the same amount. Let's find the next one. What percent of 182 is 82? Again, we'll do what question mark times 182 equals 82. The unknown value is going to be 82 divided by 182, which will reduce to, using a calculator or using long division, you get 182 divided by that gives you 41 over 91, which as a decimal comes out to be approximately 0.4505. This, however, is not the same percentage of increase. So this is going to give us 45.1%. These are not the same amount. Therefore, this is not an exponential. It's also not linear because it's changing by a different amount each time. Therefore, this equation is neither. Let's look at the next problem. In this problem, the question is, determine whether the table could represent a function that is linear, exponential, or neither. We'll do the same thing here, where we'll ask the questions, what percent of 100 is 5? When we ask that question, we have an unknown value times 100, which equals 5. If we divide, we end up with the unknown being 5 out of 100, which reduces to 1 out of 20. Percentage-wise, 1 out of 20 is 5%. Now let's take a look at the next pair. What percent of 2,000 is 100? When we do this ratio, we have the unknown ratio times 2,000, which equals 100. This is going to give us the unknown equal to 100 divided by 2,000, which also reduces to 1 divided by 20, the same 5%. This is the same amount. And you'll find if you do the final one as well, that you get the same value. In this case, if we apply it to the last one, we would be taking 2,000 and dividing by 40,000, and we would get the same percentage increase. In other words, the same 5% increase each time means that this one must be, in fact, exponential. And it's got to be exponential growth because they're going up in value. Let's take a look at the next problem. Use the compound interest formula, A of t equal to P times 1 plus R over N to the NT power. After a certain amount of years, the value of an investment account is represented by the equation 11,250 times 1 plus 0.02 divided by 12 raised to the 120 power. Rounded to the nearest cent, what is the value of the account? Okay, we're going to need some space for this problem. So we're going to add in some space here. Rounded to the nearest cent, what is the value of the account? Well, when we're looking at what the value of the account is, we need to be able to plug this into the graphing calculator or into a regular calculator. In order to do that, what we need to do is follow the order of operations. The order of operations is Pemdas, P-E-M-D-A-S. Remember that this stands for parentheses, exponents or powers, then multiplication and division, and then addition and subtraction. The multiplication and division are done at the same time from left to right, whichever you encounter first, and so are the addition and subtraction. Students rarely mess up the addition and subtraction, but you do need to be careful about the multiplication and division. They are done in order left to right. Because parentheses have the highest order, we start in the parentheses at the 1. Passing through, I see that I've got division, which has to be done before the addition. Take your calculator and enter in the number 0.02 and hit divided by 12. That gives you 1 divided by 600. Take your 1 divided by 600 that you have now and add 1 to it. We have not dealt with the power yet. When I add 1, I get 601 over 600. This becomes the next part, 11250 or 11,250 times 601 divided by 600 raised to the 120th power. Once you have the 120th power, we need to raise what's in the calculator to the 120th. Hit your x to the y or y to the x or caret symbol to get it in the exponent, then enter 120 and hit enter. My calculator gave me the following value, 11,250 multiplied by approximately 1.221199434, and it keeps going. This is probably an irrational number that never repeats and never stops. Now take that number and multiply by 11,250. We come up with the following approximate value: 13,738, and make sure you round to 2 decimal places since this is number 49 cents. Let's take a look at the next question. What was the initial deposit made to the account? Remember, an initial deposit or an initial amount is what was there when time was 0. In the formula, the t equals 0 means that the exponent would be 0. If the exponent is 0, then the entire base, which is the parentheses 1 plus 0.02 divided by 12 raised to the 0th power, would be 1. That tells me that I would end up with $11,250 for the initial amount. That's our answer for part B. The part that is preceding the base is going to be your initial amount. In this case, the 11,250. C, how many years had the account been accumulating interest? How many years? Remember that n is the number of compounding periods in a year multiplied by the number of years. For example, if you are paying monthly on a car and you have a 3-year loan, you pay for 36 months. However, the number of years was 3 multiplied by the months, 12, that you pay, and that gives you the 36. Looking at this formula, we can see that the denominator here is 12, which means that the number of times you make a payment in a year is 12 times, which means it's monthly. We'll take the 120 and divide by 12 to find the number of years. Since I have figured out that n equals 12 and nt is equal to 120, this means that 12t equals 120, which means that t must be 10. 10 years the money has been accumulating. Let's take a look at the next problem. Using the compound interest formula again, a of t equal to p times 1 plus r over n to the nt, an account is opened with an initial deposit of $5,500 and earns 3.8% interest, compounded semi-annually. Round all answers to the nearest dollar. I don't like the term semi-annually because semi-annually could mean every 2 years, or it could mean twice a year. However, most of the time in textbooks, when they say semi-annually, they mean twice a year. So we're going to assume that they mean for semi-annually 2 times a year. If it gives us the wrong answer, then we'll know they meant once every 2 years instead, which would be half. If we assume it means twice a year for semi-annually, then we want to know how much will the account be worth in 15 years. Let's add some space and figure out the following problem. First, we need to make a record of the amounts that we have. We know our initial deposit is $5,500. That's the initial principal P. P becomes $5,500. Now we need to figure out what R, N, and T are going to be. If we're earning 3.8% interest, that's the interest rate, but it's expressed as a percentage. We need to convert from a percent to a decimal. The 2 zeros in the percent symbol and the diagonal mark stand for divide by 100. So we take the 3.8 and we divide by 100 to get the decimal number 0.38, and that's 0.038. That is the interest rate written as a decimal. We already said semi-annually means 2 times a year, And in this problem, the first part, we have t equal to 15 years. We know all the information, so let's write down the problem. A is A of 15, which would be the amount of money present after 15 years if we invest $5,500 at an annual interest rate of 0.038 divided by twice a year of compounding raised to the 2 times 15. The first thing I'm going to do is multiply the 2 by the 15. This will give me 30. So I've got $5,500 times 1 plus 0.038 divided by 2 raised to the 30th power. Now take your calculator and figure out what 0.038 divided by 2 is. 0.038 divided by 2 gives us the decimal 0.019. Add 1 to that number. Remember that you have to start inside the parentheses for the order of operation. This is going to give me the value of $5,500 multiplied by 1.019 raised to the 30th power. We're going to take the 1.019 raised to the 30th power by entering the 1.019 first, hitting the power key, and then entering 30. This gives me the 5,500 still hanging out, waiting to do something till it's its turn, multiplied by about 1.758836 and so forth. Make sure that you don't round off until the very, very end of the problem. Leave all the decimal numbers in the calculator until you get to the final answer. Then you can round off. We're at the final answer now, so we're going to take that number, whatever the calculator gave, and multiply by 5,500. When we get that value, we'll round it off to the nearest penny, since this is money. That's $9,673.60. Notice the word "and" is the decimal point when you read the number out loud. What is the next part to the question? What if the interest were compounding monthly? The only thing we need to change is the n. Instead of 2, it will be a 12. Let's recompute the values using a compounding period of monthly. So A of 15 for n equal 12 would be similar, but we can expect that because it's compounded more often, it will earn more money. And in fact, that's what we're going to see. This would be 0.038 divided by 12, but notice you also have to make it 12 up here in the power being multiplied by 15. If we take the value inside the parentheses and we find what 0.038 divided by 12 is, we should have a decimal that looks like 0.003166666666 forever and ever. Don't round that off. Enter into the calculator +1 and hit the equal. That will give you 1.0031666666. Don't round that off. Never round to the very, very end of the problem. So now you've got this number right here repeating, and you're going to raise it to the 12 times 15 power. Now, what is 12 times 15? You may want to store the previous number and then recall it later. 12 times 15 gives us 180. So now we're going to take this 180 as the power, but we need to start with our 1.003166666666. If you forgot to store it and recall it, you'll have to start over again at the 0.038 divided by 12, then add your 1, and then hit the power key and enter 180, and then hit the equals key. This will give us 5,500, which has to be done last since it's multiplication, not in parentheses, being multiplied by the 1.00316 raised to the 180th power gives us about, oops, I forgot and erased the wrong thing, my bad. So we've got 5,500 multiplied by about 1.76665, and it keeps going. Don't round that off, simply hit the times button and enter 5,500. Our approximate value this time turned out to be $9,716.71. Notice that this is more money than what we had previously when we were compounding semi-annually, which was only twice a year. Now what we want to do is compound daily and assume there are 365 days in a year. Go ahead and pause the video, work it out, and then turn the video back on to see if your answer matches mine. Here's the work that I did to get my answer. This time I went ahead and wrote down what 365 times 15 was so that I would be prepared to do the power after I got this into the calculator. And then I could raise it to the 5475 power. When I was done, I had $9,725.18, which is more than what we had compounded semi-annually and more than what we had compounded monthly. This is the beauty of compound interest, and it makes a huge, huge difference how early you start as to how much money you'll have in the end. Let's look at the next problem. In this problem, it says determine whether the following represents continuous growth, continuous decay, or neither. For continuous growth or decay, our base has to be Euler's number, which is the letter E. And yes, it is pronounced Euler, not Euler, even though it looks like Euler. In this case, we do have E as the base. That still doesn't mean it's growth or decay unless we have the variable in the power in the numerator of the power. In other words, I can't have the variable in the denominator of the power as we saw previously. I can have a fraction inside the power, but the denominator of that fraction has to be a constant. In this case, because I have E being raised to the 0.25t power, I know that this is a growth problem. Now I can circle growth. Again, how do I know that it is a growth problem? Let's compare it to one where we have a decay problem. That would be this problem right here. The easiest way to tell the difference between a growth and decay is continuous, they have base E, but growth, the power is positive, and in decay, the power is negative. See here that we have a negative 4t power. Because we have the negative, that means this one is continuous decay. Let's look back at the one we started with. Again, notice that here the power is 0.25t and the 0.25 is positive. That makes it continuous growth. Now let's look at this problem. 4,742 is the initial amount. When we're looking at the next part, the base of E tells us that it is continuous if the variable is in the numerator of the power, and it is. We have 0.5t, and recognize that that could also be written as 4,742 times E to the t divided by 2 power. But again, the 2 is in the denominator, and that's a constant. The variable has to be in the numerator. Because it's a positive, this is also going to be continuous growth. Let's look at the next problem. In this problem, we have 2,574 times E raised to a power. The power, however, is the 5.25 divided by t. And it looks a little misleading, so let's write it a little bit larger so that you can see what it would look like. In a better font type, you could see that the entire power is above the e. The denominator of the power is the variable. That means it is not continuous growth or continuous decay. In this case, it's neither. Let's take a look at the next problem. When we're dealing with continuous growth and continuous decay, remember that you need to have E as the base, and the power has to have the variable in the numerator of the power. In the next problem, we want to evaluate the function and round our answer to 4 decimal places. In this case, when we use function notation, remember this is a type of substitution which says in the function called f, not the one called G or H or Fred or Tom or Harry, we want to take and replace the variable x with -4. So f of -4 is going to be written 4 times 6 raised to the -4 power. You can write this also, since the power is negative, this could be written as 4 divided by 6 to the 4th power. 6 to the 4th power, you can use your calculator to determine that that is going to be 1,296. This gives us the value of 4 divided by 1,296 in the denominator. Now take 4 and divide by that. 4 divided by that number should give you 1 divided by 324, which is the decimal number of 0.0031 when we round to 4 decimal places. It's actually 003086, but we round to 4. Let's take a look at the next problem. In this problem, we're again evaluating the function and rounding our answer to 4 decimal places. This time, we're going to a new function called f, which is -2, all being raised to a power of 3x plus 1. So we're going to rewrite this as -2 being raised to the 3 times -2 plus 1 power. This problem is very tricky. The negative that is in front of the 2 is not a part of the base because it is not included in parentheses. Because of that, we'll treat this as if it were a -1 times the 2. This is going to be like a -1 times a 2 raised to the 3 times the -2 plus 1 power. Now 3 times -2 is -6. -6 plus 1 gives us -5. This gives us the -1 times 2 raised to the -5 power. 2 to the -5 is 1/32. So this gives me a -1 divided by 32. If you write that as a decimal number, you should come up with the following decimal. It would be -0.03125, and we could round the 2 up to a 3 to round to 4 decimal places. Let's take a look at our next problem. This is another evaluate the function problem. Round our answer to 4 decimal places. In this case, we want to go to the function now called f and replace the x with the number -1. So we take the 2.2 at the front, which will be multiplied by our base. So we can use parentheses around the 5, which is the base. Make sure that you open up a hole where the variable goes and then dump the -1 inside of it. That tells you that you've got a double negative there. Negative for the -x and another negative for the number you're substituting for x. This gives me 2.2 times the 5 being raised to a power. A double negative makes it a positive 1, plus 2 makes it 3. 5 to the third power is 125. 2.2 multiplied by 125 gives the following decimal: 275. You don't need to write the 4 decimal places since it gives an exact value. Let's take a look now at the next problem. Let's take a look at this word problem. The fox population in a certain region has an annual growth rate of 9% per year. In the year 2012, there were 24,200 foxes counted in the area. What is the fox population predicted to be in the year 2018? Round to the nearest fox. Now what we want to do is add some space because we're going to need a lot more space than what I've got right there. Because we can assume that the population is a continually growing population, we can use the continuous growth formula. The continuous growth formula is the one that says A of t is equal to the initial amount A times e to the RT power. Our initial number of foxes counted in the year 2012 was 24,200. That's what we'll let A be. So we'll write 24,200 for our initial amount in the year 2012. The next thing we want to do is we want to look at the e to the RT. E is a constant and it will stay the same. E is about 2.718. Now what about R? Our R is the interest rate, but R here is represented as a percentage, and we know that won't stay in the equation. We have to convert it into a decimal number by dividing it by 100. Remember that the percent symbol itself represents the division bar, that's the diagonal slash, and the 2 zeros in the number 100. And that gives us 0.09. So now we have the equation 24,200 e to the 0.09 times t. The unknown part that we have now is the time. In the year 2012 is when we counted and started the clock. It's now the year 2018. So the time that has elapsed is 6 years. Now we'll take the 6 years and plug 6 into the formula. We're trying to figure out what A is after 6 years of continuous population growth in the fox population. This gives us e to the 0.09 times 6 multiplied by 24,200. Your calculator will have a button on it that will do exponentials raised to a power. You have to find it. It's usually on top of the button that has an LN written on it, and next to or above or below the button that has LOG written on it. Find it. It is usually the second function. So you hit the second button and then the LN button to get e to the power. Then you're going to enter the power of 0.09 times 6. You can use parentheses to group it in most calculators. 0.09 times 6 is going to give you 0.54. When you enter e to that power, you will get about 1.7160006862, and it keeps going. We're going to leave the 24,200 to be multiplied by the final result of what we got from the exponential, which is this decimal number that I'm writing down now. Then we take the decimal number without rounding off and multiply by 24,200. This gives us an approximate value of 41,527. That is a lot of foxes. I don't know about you guys, but I'm not sure I'd want to have chickens in that area. They'd definitely be stealing a few eggs, I think. So that would be 41,527. Now, can we really have 0.37 parts of a fox? No, we really cannot. So you really need to round this off. This is going to round up or round down. If we round down, I would rewrite this as 41,527. Now let's take a look at the next problem. Jamal wants to save $46,000 for a down payment on a home. How much will he need to invest in an account with 8.3% annual percentage rate, compounding daily, in order to reach his goal in 5 years? Round to the nearest dollar. In this case, this is not continuous compounding. It says compounding daily. Compounding daily is 365 days. In order to do this, we know that he wants to end up with $46,000. That is not what he is going to invest. That's what he wants to end up with. So our amount that we want to accumulate later, that's the $46,000. What we don't know is how much money he has to invest. That's the unknown, which is P. Then we need the annual interest rate, which is 8.3%, which is the same as 0.083. Compounded daily, we'll use 365 in our class. He wants to save for 5 years. That would be the time period, 5. Remember, the formula is A equals P times 1 plus R divided by N, all raised to the N times T power. Now let's put our numbers into the equation and see if we can solve for P. This gives me $46,000 on the left equal to the unknown P times 1 plus 0.083 divided by 365 raised to the 365 times 5 power. 365 times 5 is what I'm going to do first so that I know what the number is and I'm ready to work in the calculator. It's 1,825. So this would leave P times some value raised to the 1,825 power. Now I'm going to figure out what that number is. I'm going to take my 0.083 divided by 365, and that will give me a very small decimal of 0.000227397. Now add 1 to that number so that you have about 1.000227397. Again, I'm not rounding off until I get to the very end. The next thing I want to do is I want to take this number and I want to raise it to the 1,825 power. Hit your power button, which will either say X to the Y, Y to the X, or will look like a housetop caret symbol. Raise it to the 1,825 power, and we will be able to rewrite the entire equation as 46,000 equal to the unknown principal times approximately 1.514299,298. Now that you have all that written down, we need to solve for P by dividing by that number. There is a way in your calculator to turn that number upside down. It usually looks like X to the -1 or 1 over X on your calculator. It's often found above the X squared button or near to it. If I want to take that number upside down, I could turn it upside down by raising it to the -1 power. or I can divide both sides by this number. When I divide both sides by this number, then I'm going to have to start over with the 46,000. But as long as you have enough digits written down, you should be okay, and it'll be more or less accurate. This gives me the approximate value for the principal of the following. Times the 46 or 46,000 divided by that, I'm getting roughly $30,000, 377 and 0.08601, which I'll round to 9 cents. So roughly $30,377.09. So in 5 years, he will make roughly $16,000. Imagine what you could make if you started at age 20 and started just saving a small amount of money for your entire life. The difference between starting at 20 and starting at 40 is roughly usually about $1 to $2 million. And no, I'm not joking. That's the beauty of compound interest. The earlier you start, the more rapidly it grows towards the end, and it makes a huge, huge difference. So start early. This is the end of this video. In the next video, we'll be looking at graphs of exponential functions.